Alright gang, here we go. This is for Chem 2 Unit 9. We're talking about reaction mechanisms. This is part of our kinetics unit. We're getting towards the end. This video will probably end up being pretty lengthy, so buckle in. Make sure you go to the restroom before. Check your exits. Right? Okay, so so far we've spent a lot of time talking about rate laws, right? Specifically, we talked about, our rate law is equal to K times the concentrations of reactants, and we'd have something to the n, and this would tell us the order of these guys, right? And we could tell this, so this rate law, we call it a rate law because it laws in in science are things that allow us to predict what's going to happen. Okay, and so our rate law allows us to predict the rate based off of temperature, and the temperature is taken into account with our K value and based on concentration, and there's your A and your B concentrations. All right, now the theory part of this, okay, and this is what we're going to be focusing on today, is why we observe that law. So the law does a great job of predicting exactly what the rate's going to be. Now the theory is, well, how does that actually occur in nature? So essentially what we're going to be working at here is this idea, well, you're really good now in chemistry about looking at a reaction and saying, okay, we've got these two reactants that are coming together and they're making these products, right? And you know a lot of things about what happens when this happens, but as far as you know, this area right here is kind of like this black box of magic. What goes on in here, right? We don't, exactly how does this occur? How do these go from this to this? We know a little bit about like the electrons or sharing, and like maybe they're reaching a place that's more stable in the end, but between this point inside this little box, we don't really know. Okay, so far in your knowledge of chemistry, we know the whys, our theories as to why this might occur, but how, we don't really know. Okay, so really when we talk about these reaction mechanisms, this is your first peek into, well, what is going on inside this little box here in this reaction area? What exactly is happening? And so we developed these things called reaction mechanisms, and these mechanisms is defined as a series of stepwise reactions, okay, that show how the reactants become the products. All right, so and these reaction mechanisms, okay, now reactions either occur all at once or through a series of several steps, between 2 and 4 usually. All right, and so each of these individual discrete steps are called elementary reactions, okay, elementary processes. All right, and we're going to be referring to this a lot. So these elementary processes, elementary reactions, have unique properties that make them very helpful when we're determining reaction mechanisms. All right, each elementary reaction has a different molecularity. Molecularity is just a fancy way of saying, well, how many molecules or how many formula units are reacting in that elementary reaction. So if there's only one particle reacting in that reaction, we call this unimolecular. Okay. All right, and so like this would be what it would look like. This is your elementary reaction. A yields the products. All right, and so its rate law would just be equal to this. Now notice that we can, on all of these, we can just go ahead and say, well, whatever the coefficient is, that's the order. And that's the power of using elementary reactions, is that their rate law can be based off their stoichiometry. Whereas, remember before, in regular chemical reactions that are not elementary reactions, our rate law is not necessarily the same as the stoichiometry. Okay, so bimolecular reactions, bi means two, so we've got two different things that are running into each other. All right, and so these two guys hit each other, and notice that there's two of them, so this could be, the same thing as saying like there's 2A yielding the products. All right, and so it'd be the same thing as the rate equals K times the concentration of A squared. Okay, and then the other bimolecular, these are both bimolecular, even if it's the same one hitting itself or two different things hitting each other, and then its rate law would be here. All right, and then termolecular would be, 3. Okay, ter for 3, and then again the three things hitting each other, so you could have Ka cubed, or you could have Ka squared times B, or you could have K times A times B times C. All right, and so this is essentially tells us, the molecularity tells us how many molecules are involved with that step. Okay, so unimolecular 1 by 2. Ter 3. All right, and so termolecular is really as high as we ever care about. There are 4 molecular, I believe they're called tetramolecular, but they're super, super rare, because essentially what has to happen at each of these steps is these are the things that have to hit each other in the correct orientation with enough energy in order for your reaction to occur. Right. So in order for this to actually occur, you need all three of these. So if you have a termolecular step, that means all three of these things have to hit each other in the correct orientation and with enough energy for your reaction to occur. So because of that, termolecular steps are really rare. They're pretty rare. All right. And they almost are always slower than unimolecular and bimolecular. And here they go so far to say must be slower than. And that makes sense because it makes sense that if you need two things to run into each other, that would be a lot rarer than having one, or two. Or if you need three things to run each other, that would be a lot more rare, statistically, than having one or two things run into each other. Okay, and so nearly all mechanisms use only unimolecular, bimolecular reactions. Every once in a while, you have termolecular, but they're pretty rare. All right, so now that we know about elementary reactions, we need to determine, well, what determines the rate? And the thing that determines the rate is what's called the rate determining step. And the rate determining step is always the slowest step. Okay, your reaction can never, ever go faster than the slowest reaction. You're just stuck there. So if you imagine this case where you're driving a car and you're trying to get through this toll series where you've got toll A and toll B, all right, if toll A is your slow step, okay, your cars get backed up here, and then they'll get stopped briefly at B, but the rate of how fast it can leave the toll area here is purely determined on how fast it can get through toll A. It doesn't matter if these trade places, right, or anything like that. The A is always going to be your rate determining steps, and we can see the same thing here. They've just flip-flopped it. Toll B, okay, is your rate determining step. You can't get through here any faster than what you can go through toll B. No matter how fast you pile up this way, you can't ever go faster than what you can go through this way. And you can imagine also this way if you're using like funnels, right? So if you use a series of funnels and you're pouring water in, okay, and you've got one that's got a really, really tiny hole in it, okay, like this. No matter how fast you pour water into this one, you're never going to be able to go faster than what can come out the other side. All right. So you're stuck by the rate determining step. So that's an important thing as we move forward here. Okay. So what is required for a plausible mechanism? Now this is very important. You need to be able to walk yourself through these. So I'm gonna, at different points, you're going to be given, all right, possible rate or reaction mechanisms, and you need to be able to walk yourself through whether or not that is a possible reaction mechanism. All right. So the rate law, okay, number one, the rate law must be able to be devised from the rate determining step. Okay, so this is the slow step. All right, and we'll talk about what that means here in a couple of times. All right, the stoichiometry must be obtained when all steps are added up. Again, we'll talk about what this means. Essentially, your reactions, all your elementary reactions, need to be added up in order to equal your overall reaction. Each step must be balanced. You must have no intermediates left over, so essentially anything that you make needs to be used up in a following reaction that doesn't appear in your overall reaction. And then if you use a catalyst, if there's a catalyst added, you need to use it in the first step and then regenerate it as a product somewhere else. All right. So a mechanism with a slow initial step. So this is your first foray. So we've got this overall reaction here. NO2 plus CO yields NO and CO2. This is experimentally they found this rate law. Okay. All right, so and you've been able to do this a couple times. We can do it, we did it in the lab, or you can do it based on concentrations. We can do it by measuring the concentration change over time. We did it with absorbance. Okay, and so this is your rate law. Rate equals K, and that's your reaction constant, times the concentration of NO2 quantity squared. All right, and it tells you that if the first step is the rate determining step, that means that the coefficients of the reactant side need to be the same as the order in the rate law. Well, what does that mean here? If this is your rate determining step, okay, that means that you remember the first rule of defining whether or not you have a plausible mechanism is that your rate law must be able to be devised from the rate determining step. So if your first step is the rate determining step, that means this has to have come from that first step of your reaction, which means this too implies that your first step had to have had two NO2s in it. Okay, so your first step of the mechanism has to be this guy right here. Okay, so that's your rate here. Now, what would this make? Well, one thing that it could make is your nitrogen monoxide, and we know that from this right here, and this is a product. So we'll go ahead and make that product, so that makes super sense, right? And then what would be left over? Well, what would be left over would be an NO3. Okay, and so we'd have that NO3. So we decided we started with this because we know this is the first step and it's the slow step, all right? We know that because we're just making that assumption for this example here. And whenever you're starting, this is whenever you're making your own reaction mechanisms, you always kind of have to make an assumption to start. It's kind of like doing a Sudoku puzzle. All right, so you do this guy here, all right, and then we assume that we're going to make NO and NO3. We decided we're going to make NO because that's one of our products, and that just makes sense. All right, so here's the step we just came up with. So this is the easiest way to make that first step, and it's to make one of the products. All right. Now notice that NO3 does not appear in our overall reaction. We don't have NO3 here. So that means NO3 is an intermediate. And remember, intermediates must be that any intermediates we make must be used up. All right. So we need to use that NO3 later. All right. So we're going to use that NO3 here as a reactant. Okay. And we'll stick that guy with the other reactant from our overall reaction. So here's our CO. And so we'll stick our NO3 with this CO right here. Okay, and so it becomes NO3 plus CO, and that'll make us, we need to make a CO2 because that's our other product, and then what's left over is this NO2. Okay, so right now what we have is our two steps, and I'll just take the same reaction step right here, and I'll line it up right here, NO2 plus NO2, all right, yields NO plus NO3, all right. And so now we have to make sure that this makes our total balanced equation. So essentially all we're going to do is we're going to add this together just like you would in algebra and cancel out things that appear on both sides of the reaction. So here you've got an NO2 and you've got an NO2 on the product side here, so they cancel. And you've got an NO2 and nothing to cancel here, and you've got an NO3 and an NO3 to cancel. And so then what's left is you got an NO2 plus a CO yields an NO plus a CO2. Right, and so there's your reaction, right? And this is exactly the same thing as what we had. So this fulfills our second requirement of whether or not we have a plausible reaction. Okay, the stoichiometry must be obtained when all steps are added up. So we made this same overall equation when we added up all our individual steps. Okay. So since the first law is the slow steps, it matches the rate law, so we're good there. And if you add up all the individual steps, you get the stoichiometry. Each step balances, and therefore this would be a plausible mechanism. Okay. Now, how would we determine whether or not we have a plausible mechanism? So let's take a second to look at our intermediates. What exactly is an intermediate? So here we've got our reaction energy diagram, and we've talked about this before, right? And we've talked about how you have your reactants, and we meet our activation energy to meet this transition state or activated complex. Okay. And here, notice that there's two humps, one for each of our reaction steps. So in this first one, okay, this is where we did this reaction here. The NO2 plus NO2 makes to NO and NO3. And so here's would be our intermediates would be the NO3 right here, all right, from the first reaction. Really, this could be any reaction that has two steps, all right. Also notice that it makes sense here that the first reaction has the slowest because it's got the biggest activation energy. It's way bigger than the second one. The activation energy for the second reaction would only be from here to here. Okay, that would be the activation energy down here somewhere. But that would be the activation energy for the second step. This would be the activation energy of the first step from here to here. Okay, so anyway, so here's our intermediate. And notice intermediates are not the same thing as transition states. They are stable. They're just not as stable as the products or the reactants usually. All right. So what we could do is, in order to test to see if this is a valid mechanism, is if we could freeze this reaction, somehow just stop this reaction in its tracks and isolate the NO3, we could freeze it and test whether or not we actually made NO3. NO3 has its own reactivity, so we could put it through some reactions just to see if we actually made NO3 like we predicted. All right. So now let's try again. All right, this time we're going to try one with a fast initial step. All right, so this is for a reaction that looks like this. We've got nitrogen monoxide reacting with bromine, forming two NOBRs. All right, here we haven't seen these before. This is for an equilibrium. You probably saw these in Chem 1. Okay, so this means, again, that once we've reached equilibrium, okay, that means the forward and reverse reaction rates are equal to one another. It's going just as fast in the forward reaction as it is in the reverse reaction. Okay, so the rate law, okay, is found to be this. And again, they did this experimentally. Here's your rate law. It looks like this. Okay, now notice that if it only occurred in one step, all right, then that means our rate law says that it would have to be termolecular. All right, and remember, termoleculars are never ever elementary reactions. Okay, so this implies that we have a multi-step mechanism. So let's try to imagine what that could be. All right. Okay, so because it's a reaction, or because it's in equilibrium, this would be our first step. Okay, so we've got so this rate law indicates, all right, that we've got a fast step. So this would be our fast step. Any equilibrium is always a fast step. All right, so this would be a fast step, and this would be a slow step. Okay, let me just make sure. So if you, oops, okay, sorry. So if we were going to write out the reaction energy diagram for this guy, so here's our potential energy, okay, and here's our reaction progress, okay. All right, if you were going to draw this out, here would be our reactants that we're starting with, okay, and then we'd have our products, and we don't know if this is exothermic or endothermic, so we can't quite guess, but we know that this first reaction is going to be faster, and this one is going to be slow, and we know that because it's equilibrium. But let's look at what this would imagine look like. So it would look like something like this. Okay, and it would do something like that. You could imagine that when your reaction goes and it forms this NOBr2 right here, that would be this intermediate, right? We'll call this X, and so this X appears right here. Okay, and so when we're here, you can imagine that this reaction probably goes back and forth between these two things, because all it needs in order to go to the reverse reaction is just this much activation energy, right, from here to here. That's all the activation energy it needs and then in order to go forwards, it needs this much activation energy. We don't really know what the values are. We're just making it up as we go. All right, so in order to go forward, you need this much activation energy. In order to go backwards, we need, this much activation energy from here to here. All right. So you could imagine that as we're waiting for the right reaction to occur, the right collisions to occur to make the second reaction, well, there's a lot of times where the other things will react to make it go backwards, right? And so we'll kind of flip-flop back and forth here and form an equilibrium. And so that's why we make this an equilibrium, and that's why all equilibrium steps are always fast steps. All right, so then we have our slow step, and so they would look something like this. So notice that we decided we need a slow step here because we made NOBr2, and that would have to be an intermediate. How do we know we make that guy? Well, really it's based off the fact that there's not another product we can make. Okay, so we know it has to make something. Okay, and this makes sense based on what we're combining. And to find out whether or not we actually made that, again, we could just freeze this reaction and test for it. There's different tests we could actually do for NOBr2 to see if we actually make it. Then we react it with another NO, and that's just to make the stoichiometry balance out to make 2 NOBr. All right. Okay, and again, we could actually, we could add these guys up and figure out whether or not it actually makes the overall reaction. All right, and I'll let you do that on your own. Okay. So what is the rate law? Well, the rate law of the overall reaction depends on the rate of the slow step. We already established that. So the rate law for the slow step would be this, right? Our slow step was NOBr2 plus NO yields 2 NOBr. All right, there's our slow step. So the rate law would look like this. Notice we use 2 because this is the second step of our reaction mechanism. But notice that this reaction here, we can't use this as the rate law for the overall reaction because the overall reaction did not have NOBr2 in it as a reactant. Okay, there's no NOBr2 here. So we can't use it. It's an intermediate. We can't use this as our overall reaction rate or our overall rate law. Okay, so we need to be able to replace this. And in order to do this, we're going to do some fancy math. Okay, so we know that, so let's rewrite out, just to make things a little easier, let's rewrite. So it would be NO plus BR2 is in equilibrium with, I'm so sorry, I keep going the wrong way, is equal to NOBr2, all right? Now, we know when we form NOBr2, this NOBr2 could either react here, okay, and go backwards to form these reactants, or it could react in the forward reaction to form NOBr2, right? These are our two options. The NOBr2 could go this way, or it could go to here, all right? And because of that, all right, we know that those are the two options that it can go through, okay? And so the NOBr2, all right, if it goes forwards, right, if it goes, the reaction rate, because this is an elementary step, right, our rate would be equal to K1, right, and we use 1 because that's our first one, times the reaction of NO times the reaction of Br2. All right, and if we were going to react backwards, so that let's just rewrite this backwards just to help us picture it a little better. Okay, so this is the same thing, just written backwards. All right, that would be equal to NO plus Br2. So the rate of this guy, and this is the reverse of the first reaction, so we call this -1, okay, and that would be equal to just the concentration of NOBr2. Now, if you think to yourself, all right, this is in equilibrium, and the definition of equilibrium is that our reaction is, the rate of reaction is equal in both directions, that means these rates have to be equal to each other. So we can set these guys equal to each other. So that means our K1 times the NO times Br2, right, is equal to K minus 1 times NOBr2. Okay? All right, so that makes sense, right? Because we're at equilibrium, so these two have to be equal to each other. And then it'd be easy enough. Well, all we have to do, if this is our rate law and the problem is this guy, we can solve for NOBr2. So that means the concentration of NOBr2, all right, the concentration of NOBr2 would be equal to K1 divided by K minus 1 times the concentration of NO times the concentration of Br2. All right. And then it's just a simple matter of replacing our NOBr2 with all of this. Okay, so we just take this guy to plug this in here. Okay, and so therefore our rate of our overall reaction would be equal to K2 times K1 over K minus 1 times NO times Br2 times concentration of Br2. Okay, that's all this. Okay, times the concentration of NO. All right, and then because all these are K's and all these are just individual rate steps, our overall rate law would turn into rate of the K of the overall reaction, which we just call K, times the concentration of NO squared, right, because it's that, times the concentration of Br2. And there you go. That's your rate law, and that's exactly what we found up here experimentally, NO squared times Br2. All right, so this is what we mean by that phrase. Let's go back to our rules for reaction mechanisms. This is what we mean when we say that the rate law must be able to be devised from the rate determining step. We started with the slow step, and we did algebra in order to find the rate law. Okay. So let's do some practice problems. Okay. It says consider the following two-step reaction mechanism. Maybe, go. All right, so we got A plus B yields X plus Y, and then X plus C yields Y plus Z. It says which of the following statements about this mechanism is or are true. All right, it says both of these reaction steps in this mechanism are bimolecular. Well, bi means two, and there's two molecules, so yeah. All right, so they're both bimolecular. It says the overall reaction is A plus B plus C yields Y plus Z. Well, let's try it. So we're just going to add this guy up. So A, there's nothing to cancel, so we'd have an A. B, there's nothing to cancel. X would cancel with our X, and then we're good. So this would become A plus B plus C yields, and then we've got two Y's, so 2Y plus Z. All right, that's my Z there. Okay, notice we've got two Y's, so there's no two Y's here, so no, that's no good. All right, this should have a 2. All right, right here. Okay, and the substance X is an intermediate in this reaction. Well, an intermediate is something that we form in one step, use up in another. So yes, yeah. So 1 and 3 are true, so be C. All right. Let's try this one here. Okay. Whoop. For the reaction, this monstrosity, the proposed mechanism is this. All right. Is the proposed mechanism consistent with the equation for the overall reaction? All right, well, let's see. So we just do the same thing here. We just cancel things out. So MOCR, so nothing cancels. All right, so this would cancel here, this would cancel here, and then you're good. So you'd have this and this as reactants, and this is products. So yeah, yes, it is. Okay, what is the molecularity of each step? Well, this is just one thing, so this would be unimolecular, and then this is two things, so this would be bimolecular. All right, it says identify the intermediates. Well, the only intermediate, that would be the thing we crossed out, so that would just be MOCO5. Easy peasy. Okay, now predicting the rate law for an elementary reaction. Well, we've already done this a couple of times. So it says if the following reaction is a single elementary reaction, predict its rate law. Well, this is easy. So it's just rate is equal to K times the concentration of H2 times the concentration of Br2. Okay, and I think they get the same thing. There it is right there. And then it's interesting, they say that it actually shows that experimentally the rate law looks something like this. So that shows that it cannot be an elementary reaction, that there's something else going on. It's at least two elementary steps making that mechanism. And you can do a little bit of experimentation to figure out what that is. All right, let's try this guy here. All right, it says consider the following reaction: 2a plus b yields x plus 2y. You are told that the first step in the mechanism of this reaction has the following rate law. All right, so there's your rate law. Okay, notice that it does not match this. Okay, so that means for sure that this is not an elementary reaction. And that also makes sense because this would be termolecular, which is never an elementary reaction. It says, which of the following could be the first step in the reaction mechanism? Note the substance Z is an intermediate. All right, so the easiest way to do this is just assume that this would be the slow step. Okay, and that also makes sense because there's it's just A times B, so that means our, if we could find one of these that's simply A plus B reacting to form a product in Z, we should be good. All right, so this doesn't match our slow step, so we'll kick this guy out. All right, let's see what else. And then this doesn't match our slow step, this doesn't match our slow step, this doesn't match, so it's got to be E. All right, the other way you could kind of look at it here is that, wait, there was something else I thought of. I don't remember what it was. All right, whatever. Then it says, consider the following reaction. This goes to this. Write the rate law for the reaction, assuming it involves a single elementary reaction. So that would be rate is equal to times NO squared times BR2. Okay. Is a single step mechanism likely for this reaction? Well, no way. It's termolecular. Nope. All right. So here's where the rubber meets the road. Okay. Determining the rate law for multi-step reaction. Never mind. All right, well, let's do this. The decomposition of nitrous oxide is believed to occur by its two-step mechanism. So you got N2O yields N2 plus O, and that's your slow step, they said. And then N2O plus O yields N2 plus O2, and that's your fast step. Write the equation for the overall reaction. All right. So first, we're just going to cancel out all our guys here. Okay. All right. And so they got this as their overall reaction. Okay, all they did was, cancel out your N2, or your N2s combined, so you get two N2s. You got your N2O and an N2O, those two combined, and you got an oxygen on both sides. All right, so they cancel. All right. And then part B asks us write the rate law for the overall reaction. Well, based on the slow step, the rate law of the slow reaction would be equal to K times the concentration of N2O. All right. And since this is in the reaction, overall reaction, we should be good. That's really all we need to do. Okay, it's right there. Okay, the rate law for the overall reaction is just the rate law for the slow rate determining step, because the slow step is unimolecular elementary reaction. The rate law is first order. All right. Let's do this one here. Ozone reacts with nitrogen dioxide to produce dinitrogen pentaoxide and oxygen. All right, the reaction is believed to occur in two steps. The experimental rate law is this. What can you say about the relative rates of the two steps of the reaction mechanism? So can you determine, which essentially they're asking, can we determine whether or not it's it's slow or fast? Or which one's the slow reaction, which one's the fast reaction? All right, so really what we can do, first thing you do is just to see whether or not there's a difference in, the molecularity. And they're both bimolecular, so really we can't tell anything by that. The second thing I would do is write out the rate laws for these two guys. So the rate of this one would be K1 times the concentration of O3 times the concentration of NO2. All right, and then the rate of this one would be the rate is equal to K2 times the concentration of NO3 times the concentration of NO2. All right, and so you can tell, number one, in order to make this guy work, we'd have to do some of that algebra magic in order to get the NO3 to go away. All right, with this one, notice that our rate law right here, is already equal to the rate law for the elementary step. So that means the first step has to be the slow step. Okay, because it matches the rate law, and the rate law has to be based off the slow step. All right, now this is where the rubber meets the road. All right. It says, show that the following mechanism for equation 14.26 also produces a rate law consistent with the following experimentally observed one. So this is the one that the experiments actually match up with. So we got, and in this particular one, we got NO plus NO yields N2O2. Okay, and then N2O2 plus Br2 yields N2NOBr. And so we've got a fast equilibrium step as opposed to the slow one we had earlier with this specific reaction. So it gives us a mechanism with a fast initial step, and we have to write the rate law. So what we have to do is a little bit of algebra magic here in order to make it work. All right, so The second step would be our rate determining step, okay, because it's the slow step. So this is what our rate law for the second step would be equal to. However, our overall reaction did not have N2O2 in it. This would be an intermediate based on this reaction mechanism. So we're going to have to do some fancy magic, just like we did earlier. All right, and so this is what they get here. All right, so again, they use their equilibrium, so these two are equal to each other, and then they solve for N2O2, okay, and then they plug that back in, and so you end up with this one. All right, and then this mechanism also yields a rate law consistent with the experimental one. Okay, and so the only way to determine whether or not this mechanism is better than the one that we came up with earlier is by actually doing experimentations to figure out whether or not we actually made whichever intermediate, because that's really the only difference, right? Is that intermediate, one of the intermediates, we form this N2O2, and the other one we form the other. Okay. All right. Consider the following hypothetical reaction. This will be it. All right. Get our arrows to show up here. All right, it says, consider the following hypothetical reaction. 2p plus q yields 2r plus s. All right, the following mechanism is proposed for this reaction. All right, so we got a fast initial step that's at equilibrium. We got q plus d yields r plus u, and u yields r plus s. All right, and the middle step is our slow step. Okay, substances T and U are unstable intermediates. What rate law is predicted by this mechanism? All right, so what we're going to start with is we're going to start with this reaction in the middle, because that's our slow step. All right, so that means our rate, okay, of K2 would be equal to concentration of Q times concentration of T, right? But we can't stop there, because T is not in our overall reaction, right? T is not here, so we can't have T in our rate law. So we got to figure out a way to get rid of T. Well, T appears in this one here, okay? And hopefully we've established by now that because we're at equilibrium, these rates would be equal to each other. Okay, so that means, let's see, I'll do this one over here. So that means our K1 times P squared, all right, would be equal to K minus 1 times concentration of T. Right, and we can divide this over, so K1 over K minus 1 is equal to P squared. That's equal to concentration of T. So now we can take this and we can plug this in here. So our rate of our reaction would be equal to K2 times K1 over K minus 1 times Q times our concentration of P squared. And then all this would just become K, right? All this just becomes K. So hopefully we have a P squared Q. P squared, almost PQ, P squared Q, so this is going to be it. All right. And that's it. So next video here, we'll talk about catalysts. Should be a lot of fun. This stuff can be pretty tricky, so make sure you do lots of practice problems. Let me know if you have any questions, and I'll see you on the flip side.